about the, frankly, mind-boggling tech that lets you ask your phone a question or get that perfect code suggestion. Today, we're doing a deep dive into exactly that, the fascinating world of language models, especially the large language models you hear so much about. We've been digging into the 100-page language models book by Andriy Burkov, and we're here to pull out the most crucial insights for you.
Absolutely. Our goal today is really to trace that journey, how machines actually learned to understand and, generate human language from the very basics right up to the cutting edge. We'll unpack the core ideas, try to demystify some of the, let's call it magic of deep learning, and show you what makes these models so powerful, but also, importantly, what their limits are. It's about getting to those aha moments without getting lost in the weeds.
Exactly. Well, look at the history, those early AI winters people talk about. We'll get into the mathematical nuts and bolts, how these things are trained, and, how they actually manage to talk like us and help with things like writing or coding. Okay, let's get into it. So let's start right at the beginning. The roots of AI. A lot of people probably don't realize the term artificial intelligence itself was coined way back in 1955. It was during this workshop led by John McCarthy. They were really ambitious, trying to figure out how machines could actually use language, form concepts, solve problems like humans do.
Yeah, that workshop really set the stage, and some fascinating early work came out soon after. You had the logic theorist in '56, arguably the first program that could do automated reasoning. Then Frank Rosenblatt's perceptron in '58, a very early neural network trying to recognize patterns, and of course, ELIZA in '67, Joseph Weissenbaum's chatbot. It was simple, but it really captured the public imagination, this idea of a machine that seemed to understand you. But that initial burst of optimism, well, it didn't last. It led to these AI winters, periods like 75, 80, and again 87, 2000, where funding just dried up. The problems turned out to be way harder than expected. Promises weren't met.
Right. So jumping ahead a bit, when we talk about a model in machine learning today, what are we actually talking about? For our listeners who get the basics, it's like a mathematical function, y equals fx, right?
Exactly. The whole game is to build that function f by learning from a data set of examples. So you give it new inputs, x, and it produces meaningful outputs, y. For simple linear functions, maybe like fx of ux plus b, those w and b values are the parameters or weights the model learns.
And how does it learn them? You mentioned supervised learning has steps.
Yeah, typically 4 main steps in supervised learning. First, you collect your data, say, pairs of house square footage and price. Second, you define the model structure, like that linear equation y equals wx plus b. Third, you need a loss function. This measures how long your predictions are. Mean squared error is a common one. It just squares the difference between the predicted price and the real price. And fourth, the crucial step. You minimize that loss across your whole data set. Find the w and b that make the errors as small as possible. Now, for simple models, you might solve this with math. But for models with millions or billions of parameters, forget doing it by hand.
Okay, so complexity ramps up quickly. What happens when you have more than one input feature, like house area and number of bedrooms?
That's where vectors come in. Your input x becomes a feature vector, just a list of numbers representing area, bedrooms, maybe location. And this naturally leads to using linear algebra vectors and matrices because it's super efficient for computation. A really useful concept here is cosine similarity. It measures how similar two vectors are, basically the angle between them. It's used all the time to compare word meanings.
But the real world isn't always linear, is it? Predicting house prices might be roughly linear, but language seems way more complex.
Absolutely right. Simple linear models hit a wall pretty fast. That's why neural networks were such a breakthrough. They introduced nonlinearity. They take the output of a linear function and pass it through a fixed nonlinear function called an incubation function, things like ReLU, sigmoid, or ton. And crucially, they stack these operations in layers, making the network deep. This hierarchical structure lets them learn incredibly complex nonlinear patterns that simple models just can't capture. That's key for understanding language.
So you have these deep, complex networks. How do they actually learn? How do they adjust those millions of parameters? You mentioned minimizing loss, but how?
Right. The core mechanism is usually an iterative process called gradient descent. Imagine you're standing on a complex, hilly landscape in the fog, and you want to find the lowest valley. Gradient descent is like taking small steps in the direction of the steepest downward slope you can feel right where you are.
Okay. Makes intuitive sense.
Mathematically, it uses the gradient of the loss function. The gradient is just a vector pointing in the direction of the steepest increase in loss. So you calculate that gradient, and then you nudge your parameters, the weights and biases, in the opposite direction. downhill. You repeat this over and over. The learning rate is a hyperparameter that controls how big each step is. And this is absolutely essential because calculating these gradients manually for, say, 1 billion parameters, impossible. It would take forever.
Which brings us to automatic differentiation.
Exactly. This was the real enabler for modern deep learning at scale. Before libraries like PyTorch or TensorFlow, researchers literally had to derive these complex gradients by hand using calculus. It was painstaking and incredibly error-prone. Automatic differentiation frameworks build a computational graph, tracking all the operations as data flows forward through the network. Then, they can automatically compute all the necessary derivatives for the backward pass, where the learning happens. It means you can swap out layers, change architectures, experiment wildly. As long as you use the library's building blocks, the gradient calculation is handled for you. It completely changed the game.
Okay, so we have the learning mechanism. Now let's focus back on language. How do you even get text into a format these number-crunching models can use?
Right, that's a fundamental challenge. An early simple approach was the bag of words method. First step. Build a vocabulary. Just list every unique word across all your documents, your corpus. Second step, represent each document as a vector. Each dimension in the vector corresponds to a word in the vocabulary. The value could be just 1 or 0, did the word appear, or its frequency, how many times.
Simple enough, but I can already see problems.
Oh yeah, major limitations. The biggest, it completely ignores word order. So the cat chased the dog and the dog chased the cat look exactly the same to a bag of words model, even though their meaning is opposite. It also chimped on out-of-vocabulary words it hadn't seen during vocabulary creation, and it had no concept of synonyms. Movie and film were just two completely different, unrelated dimensions in the vector space.
So that needed fixing. What came next?
The big leap was word embeddings. This is a really clever idea. Instead of these sparse, mostly 0 vectors, words were mapped to dense vectors, shorter vectors, maybe a few hundred dimensions, with mostly non-zero values. And the magic was, these embeddings were learned by neural networks in such a way that semantically similar words ended up with vectors that were close together in this space, having high cosine similarity. Word2Vec was a famous algorithm for this. It revealed these amazing geometric relationships, like you could take the vector for king, subtract man, add woman, and the resulting vector was closest to the vector for queen. Mind-blowing stuff.
Wow, so the network learns meaning from context.
Exactly. Learned from massive amounts of unlabeled text data. But even with embeddings, handling huge vocabularies, especially in languages with lots of word forms, was tricky. Think Finnish nouns having thousands of forms. That's where byte pair encoding, or BPE, came in. It was originally a data compression trick. For NLP, it works by starting with individual characters and iteratively merging the most frequent pairs of characters or character sequences to form subwords. You keep doing this until you reach a target vocabulary size, maybe 30,000 or 50,000 subword units. This helps keep vocabulary manageable, and crucially, it can represent almost any word, even new ones, by breaking them down into known subwords. It handles the OOV problem much better.
Okay, words are now numbers, specifically dense vectors or subword vectors. So what exactly is a language model? What's its core job?
At its heart, a language model predicts the next token, which could be a word or a subword in a sequence. It estimates the probability of a token appearing, given the tokens that came before it. Phi next token, preceding tokens. This fundamental ability is what powers text generation, machine translation, summarization. Lots of tasks. We often call these autoregressive or causal language models because the prediction depends only on past context.
Before neural nets dominated, how did they do this?
They used count-based language models. Simpler, statistically driven. For example, a trigram model would estimate the probability of the next word based only on the previous 2 words. It would literally count how many times that specific 3-word sequence appeared in a huge training text corpus and divide by how often the 2-word prefix appeared. If a specific trigram was never seen, they used tricks like back off, falling back to the bigram probability, or even the unigram single word probability.
I remember those on old phones. Autocomplete felt like magic then. But yeah, limited.
Exactly. Useful for things like autocomplete, but they had big drawbacks. Still struggled with unseen word sequences, OOV problem again. And critically, they couldn't capture long-range dependencies. The meaning of a word might depend on something said many sentences ago, but a trigram model only looks back 2 GERDs. Trying to extend these count-based models to look back thousands of tokens, the memory requirements would be astronomical, just wouldn't work.
So how do we even measure if one language model is better than another?
A standard metric is perplexity. It's a bit abstract, but essentially it measures how well the model predicts a sample text. Lower perplexity means the model is less surprised by the text, meaning its predictions are more confident and accurate, so lower is better. For reference, that count-based trigram model we mentioned might have a perplexity around 300. An early but significant neuromodel like GPT-2 got it down to about 20. Modern LLMs. They're achieving perplexity scores below 5 on standard benchmarks. It's a huge leap. For specific tasks like summarization, we also use metrics like ROUGE, which compare generated text to human references. But honestly, automated metrics don't capture everything. Nuances like fluency, coherence, factual accuracy, for those, human evaluation is still essential. People rating outputs on Likert scales or ranking them using Elo systems.
Okay, moving into the neural network era for language. What were the key architectures before transformers took over?
Recurrent neural networks, or RNNs, were the dominant approach for a long time. Unlike standard feed-forward networks, RNNs have loops. Connections feed back into the network. This allows them to maintain a hidden state. Think of it as a memory vector that gets updated at each step as they process a sequence token by token. This state carries information from previous tokens forward, allowing them to handle sequential context much better than earlier models.
So they process word by word, updating their memory.
Precisely. The Elman RNN from 1990 was a classic example. It took an embedding vector for the current word, combined it with the hidden state from the previous step, and produced an output and a new hidden state for the next step. This sequential nature was powerful, but RNNs had a major problem. They struggled to remember information over very long sequences. The influence of early tokens tended to fade away. The dreaded vanishing gradient problem was also a big issue for training deep RNNs. There's actually renewed interest now with things like MinLSTM and XLSTM, but for a while, RNNs were largely eclipsed by
the transformer. This seems to be where everything changed.
Absolutely. The 2017 paper Attention is All You Need introduced the transformer, and it just revolutionized sequence processing, especially NLP. Its core innovation is the self-attention mechanism. Instead of processing tokens sequentially like an RNN, self-attention looks at all the tokens in the input sequence at the same time. Each token can directly calculate how relevant every other token in the sequence is to understanding its own meaning and context.
So every word looks at every other word simultaneously.
Yeah.
How does that work?
It's clever. For each input token, represented by its embedding, the model learns to generate 3 different vectors: a query, Q, a key, K, and a value, V. Think of the query as asking, what information do I need? Think of the key as saying, here's the kind of information I represent, and the value is, here's the actual information content. Then, for a given token, its query vector is compared, usually via dot product, with the key vectors of all tokens in the sequence, including itself. This comparison gives you attention scores. How much attention should this token pay to every other token? These scores get scaled, divided by the square root of the key vector dimension just to stabilize training. Then, crucially for generation, a causal mask is applied. This prevents a token from attending to future tokens during training, ensuring it only uses past information to predict the next token. Finally, these masked scaled scores are turned into probabilities, weight summing to 1 using a softmax function. And the output for our token is a weighted sum of all the value vectors, using these attention probabilities as the weights. It's a dynamic, context-dependent representation.
Okay, wow. That's intricate. But if it processes everything in parallel, how does it know if cat chase dog is different from dog chase cat? How does it get word order?
Great question. That's where positional embeddings come in. Since self-attention itself doesn't care about order, you need to explicitly inject position information. Early transformers added learned or fixed vectors representing position to the input embeddings. A more modern and effective technique mentioned in the book is Rotary Position Embedding, or ROPE. ROPE encodes position by applying rotations to the query and key vectors, where the angle of rotation depends on the token's position in the sequence. It's mathematically elegant. And a key advantage of ROPE is that it seems to generalize much better to sequence lengths longer than those seen during training, which is hugely important now.
And they don't just do this once, right? There's multi-head attention.
Correct. Instead of having just one set of Q, K, V matrices, multi-head attention runs several self-attention mechanisms, heads, in parallel. Each head learns to project the input embeddings into a different subspace and can potentially focus on different types of relationships or different parts of the sequence. Maybe one head focuses on syntax, another on semantic similarity. The outputs from all these heads are then concatenated together and passed through a final linear layer, a projection matrix, to combine the information. It allows the model to capture a richer set of dependencies simultaneously. And two other crucial components for making these deep networks trainable are residual connections, or skip connections, and layer normalization, like RMS norm. Residual connections add the input of a layer directly to its output. It creates a shortcut, helping gradients flow back through very deep networks without vanishing. RMS norm helps stabilize the activations. These are essential engineering tricks.
Okay, and there's one more optimization mentioned for when the model is actually generating text.
Yes, key value hashing. This is super important for inference speed. When generating text token by token, the model needs the keys and values for all the previous tokens it has already generated to calculate attention for the next token. Instead of recomputing these K and V matrices for all preceding tokens every single time it generates a new token, which would be incredibly slow for long sequences, it caches them. It saves the K and V tensors from previous steps and just computes the K and V for the newest token, then uses the cached values for the attention calculation. Huge speed up.
So even a small transformer showed improvement over an RNN in the book's examples.
Yeah, the book built a small decoder-only transformer with about 8.6 million parameters. It achieved a perplexity of 55.19 on their test set. This was notably better than an RNN they built with a similar number of parameters, 8.2 million, which got a perplexity of 72.23. It clearly highlights the transformer's effectiveness even at a small scale, but really, their true power emerges when you scale them up dramatically.
Which leads us perfectly to the large language models. This isn't just a minor increase, is it? What defines this scale?
No, it's a massive leap across several dimensions. The book emphasizes 4 key factors. 1, parameter count, just enormous numbers of learnable weights. 2, context window size, how much text the model can process at once. 3, training dataset size, the sheer volume of text they learn from. 4, computational resources, the immense compute needed for training. It's the combination of these 4 at unprecedented levels that unlocks the really emergent, sometimes surprising capabilities.
Okay, let's break those down. Parameter count.
It's staggering. That small example model had 8.6 million parameters. Modern LLMs, we're talking hundreds of billions, even trillions in some research models. To give you a tangible sense, a 70 billion parameter model like Llama 2 70B, if you store each parameter as a standard 32-bit floating point number, that's about 280 gigabytes of just model weights. The book mentions this is over 30 million times more storage than the entire Apollo 11 guidance computer had. This vast number of parameters lets the model memorize and generalize an incredible amount of information about language, facts, reasoning patterns.
Okay, parameter count.
Huge. What about context window? This is how many tokens the model can look at simultaneously, input and output combined. Early models like GPT-3 had a context window of 2,048 tokens. That's maybe 334 pages of text. Respectable, but limited. Fast forward to models like Llama 3.1, mentioned in the book, its context window is 128,000 tokens. That's enough to fit the entire text of Harry Potter and the Sorcerer's Stone inside the context window, with room left over. It allows for much more complex instructions and retaining information over very long interactions.
But didn't you say attention is computationally expensive? How do they handle 128,000 tokens if cost grows quadratically?
That's the huge engineering challenge. Self-attention has O(n)2 complexity quadratic in the sequence length then. Doubling the context length quadruples the compute and memory needed for the attention layers. Achieving these long contexts requires specialized techniques during training, often called long context pre-training. It might involve starting with a shorter context and gradually increasing it. And during training and inference, they use clever parallelism strategies like context parallelism and efficient data gathering, all-gather, to distribute the massive attention computation across many GPUs or specialized hardware accelerators. It's a major systems problem.
Got it. Factor 3. Training data size.
Again, the scale is hard to grasp. The book's small decoder model was trained on maybe 25 million tokens. Modern LLMs are trained on datasets containing trillions of tokens. These datasets are scraped from huge swaths of the internet books like Project Gutenberg, websites like Common Crawl, scientific papers, ArtDiff, code repositories, GitHub, social media, incredibly diverse sources.
Trillions. Can you put that into perspective?
The book uses the DOLMA dataset, 3 trillion tokens, as an example. If you read 8 hours a day, every day, at a typical speed of 250 words per minute, it would take you roughly 51,000 years to read that much text. It's this vast exposure to diverse language and information that allows LLMs to learn grammar, facts, different styles, reasoning abilities. And because the data sets are so enormous, models usually only see the training data once. It's called single epoch training. Doing multiple passes would take far too long and risk overfitting.
Mind-boggling. And the last factor, computational resources.
This underpins everything else. Training these behemoths requires absolutely immense computing power, usually measured in GPU hours or equivalent units. For instance, training the Llama 3.1 series of models, according to the book's sources, consumes something like 40 million GPU hours. To put that in perspective, running one powerful GPU nonstop, that's almost 4,600 years of compute time. So you need massive clusters of thousands of GPUs, interconnected with high-speed networking. And sophisticated software, 4D parallelism is mentioned, to efficiently distribute the model parameters, the training data, and the computations across this hardware. The cost, easily tens, potentially hundreds of millions of dollars just for the training run of a single state-of-the-art model.
Wow. Okay, so all that scale parameters, context, data, compute goes into pre-training the model.
Yeah.
But you said that just makes it good at predicting the next token.
Primarily, yes. Pre-training imbues the model with vast knowledge and linguistic competence, but it's raw. It might complete text well, but it might not follow instructions reliably or converse naturally. To make it useful as a chatbot or assistant, it needs supervised fine-tuning, SFT. This involves training the pre-trained model further on a smaller, curated dataset of high-quality instruction response examples. SFT is what unlocks the capabilities learned during pre-training and teaches the model to be helpful, follow instructions, and align with desired behaviors, like being truthful and harmless. The book gives an example. A pre-trained Gemma model might just repeat sentences, but the fine-tuned version, Gemma IT for instruction tuned, correctly follows instructions to continue a list. It's a critical step.
Right, so fine-tuning makes them actually useful for specific tasks. How does that work in practice? Like classifying emotions?
Yeah, the book has a good example of fine-tuning GPT-2 for emotion classification. You create a data set of text examples paired with emotion labels like joy, sadness, anger. Then you format this as a text completion task for the model. For example, the input prompt might be, predict emotion, feel very happy emotion. You train the model to complete this prompt with the correct emotion word, joy. Even with GPT-2's relatively small 124 million parameters, this fine-tuning significantly boosted accuracy compared to a simpler baseline model, reaching over 94% on the test set. It shows how you can adapt these models.
And for general instruction following, like you see in chatbots.
The key there is the prompting format used during fine-tuning. You need a consistent structure so the model learns to distinguish between the user's instruction and its own response. Formats like Vicuna's USR on instructionassistant.solution or OpenAI's ChatML with special tokens like insert_user are common. And research like Meta's Lima paper highlighted in the book strongly suggests that the quality of the fine-tuning examples is far more important than the sheer quantity. A few thousand really well-crafted examples can lead to excellent instruction following ability.
But fine-tuning these huge models still sounds computationally expensive, even if the dataset is smaller.
It can be, especially if you try to update all billions of parameters. That's where techniques like low-rank adaptation or LoRa come in. It's a form of parameter-efficient fine-tuning, PEFT. Instead of changing the huge original weight matrices of the pre-trained model, which are kept frozen, LoRa adds two much smaller low-rank matrices alongside each one. During fine-tuning, you only train the parameters in these small LoRa matrices. They learn the changes or adaptations needed for the new task. Because these LoRa matrices are tiny compared to the original weights, the number of trainable parameters is dramatically reduced, maybe by 99% or more. You get performance very close to full fine-tuning, but with massively lower memory requirements, making it feasible to fine-tune even billion-parameter models on consumer-grade GPUs sometimes.
That's a real game changer for accessibility. So LoRa is part of this PEF idea.
Exactly. LoRa is probably the most popular PEFT method right now, and libraries like Hugging Face's PEFT library make it really easy to apply LoRa or other PEF techniques to existing models. It's democratizing the ability to customize these powerful tools.
Okay, so besides fine-tuning, there's also just talking to the models, prompt engineering. That seems like a whole skill in itself.
It absolutely is. It's the art and science of crafting input prompts that effectively guide the LLM to produce the desired output. The book breaks down key components of a good prompt. Clearly define the situation or context, specify the model's role, eventually you are an expert Python programmer, give clear task instructions, specify the desired output format, for example, JSON bullet points, state any constraints, for example, word count, tone, define quality criteria, e.g. be concise, explain your reasoning, provide examples, this is few-shot prompting and can be very effective, and finally, have a clear call to action, what the model should actually do. Thinking through these elements can make a huge difference in the quality of the response.
And it's not always perfect first time, right? What do you do then?
Rarely perfect first time. Iteration is key. Follow-up actions are crucial. You can directly ask the model to critique its own previous response. Are there any errors in the code you just provided? Or, if a conversation starts going off the rails, it's often best to just copy the relevant parts and start a fresh chat. The book suggests it's often a good idea to start fresh after maybe 3 to 5 exchanges anyway, because very long conversation histories can sometimes confuse the model or lead to errors accumulating. Context windows are big, not infinitely reliable.
What are some really practical, standout applications mentioned?
2 big ones highlighted are code generation and documentation synchronization. Since these models are pre-trained on vast amounts of code from places like GitHub, they get surprisingly good at generating code snippets, functions, classes, even whole boilerplate applications based on natural language descriptions. And for documentation, they can analyze code changes, like in a Git commit, and automatically suggest or even generate updates to the corresponding documentation, helping keep code and docs in sync. That's a huge pain point for developers. Apparently, the book's own website was built entirely through collaboration with an LLM, which is pretty meta.
That's impressive. But there's a big catch we haven't fully addressed. Hallucinations. Model just making stuff up.
Yes, this is arguably the biggest Achilles heel of current LLMs. Hallucinations are when the model generates text that sounds plausible, confident, maybe even stylistically perfect, but is factually incorrect, nonsensical, or completely fabricated. And the tricky part is, as the book notes, they are almost by design. The model's core objective during pre-training is just to predict the next statistically likely token, not to be truthful. It optimizes for fluency and coherence based on patterns in the data, not for factual accuracy. Low quality or biased training data definitely contributes, as do errors that cascade during generation laters. And one small mistake can lead the model down a completely wrong path.
And you actually fix them? Or just reduce them?
You can't eliminate them completely, not with current architectures fundamentally based on next token prediction, but you can significantly mitigate them. A very powerful technique is retrieval augmented generation, or AI. The idea is before the LLM generates a response, you use the user's query to retrieve relevant, verified information from an external knowledge base, like company documents, a database, or curated web search results. You then inject this retrieved information directly into the prompt you give the LLM, instructing it to base its answer on the provided context. This grounds the model's response in actual facts, dramatically reducing the likelihood of it fabricating information because it has the correct information right there in its context window. Another approach is domain-specific pre-training, continuing to train the model on large amounts of reliable, unlabeled documents from a specific, trustworthy domain.
Okay, that makes sense. Grounding it in facts.
It's a crucial area of research and development.
So what a journey. We've gone from those early AI concepts in the 50s through the basic math of machine learning, the rise of neural nets, RNNs, then the transformer revolution, self-attention, positional embeddings, and finally into the sheer scale of modern LLMs, the parameters, data, context, compute, and how we actually work with them through fine-tuning and prompting, while grappling with challenges like hallucinations.
Exactly. We've seen how scale unlocks these incredible capabilities, driven by clever architectural innovations and engineering feats like parameter-efficient fine-tuning. And we've touched on the ongoing work to make these models more reliable and controllable, moving them beyond just predicting text to becoming genuinely useful reasoning engines. It's really about understanding both the power and the pitfalls.
You should now have a much clearer picture, a solid technical foundation, for understanding how these models work and appreciating what they can do.
Yeah.
It really does feel almost magical sometimes seeing how machines can learn to process language this way.
It does. And it leaves us with a thought, maybe drawing inspiration from Antoine de Saint-Exupéry, who wrote something like, "Language is the source of misunderstandings." If that holds true for humans, as these incredibly fluent but sometimes subtly flawed language models become woven ever deeper into our communication, our work, our lives, what new kinds of clarity might they bring? And what new, perhaps unexpected, forms of misunderstanding or confusion might emerge? Something to think about.
Definitely something to ponder. We really hope this deep dive has given you a new perspective and maybe even sparked some curiosity to explore further.